Welcome back. In the previous lecture, we established the equations of motion by Schrödinger for kets and bras and by Heisenberg for operators. In this lecture, we studied the time dependence of the probability amplitudes of a qubit with the Schrödinger equation. We talked about these Schrödinger equations, one for the bras and one for the kets, and a Heisenberg equation for the operators. Now, of course, although I wrote Heisenberg equation singular, this is really not one equation. It's one such equation for every observable A that we can think of and every physical system characterized by the Hamilton operator H. And same here. I mean, it's two equations as written, one for bras and one for kets. But again, this is many different bras, many different kets, many different physical systems. Now, the main application of the Schrödinger equation is not so much for the kets and bras, but for wave functions. Now, let's remember what these wave functions are. Well, these wave functions are made of components, and these components are probability amplitudes. So we will ask in a short while, what is the time dependence of a probability amplitude? But to set the stage, we will just look at an example that is simple enough to go through it in detail, but not too simple. So we will still be able to understand a lot of general features about wave functions, Schrödinger's equation, Heisenberg equation, and so forth. And then after studying this simple example, we will go to the more general case. So the example that I have in mind is a binary quantum system. For example, you can think of an atom where two of its energy levels are important. The ground state, which I denote by G, and the excited state, for which I denote by E. So if the atom is in the ground state at some time, well, there will be a ket or a bra that goes for the ground state and the time t that we are talking about. So there is a bra and a ket. And same for the excited state. So an excited state bra and an excited state ket. And they depend on time, because it matters which time we are talking about. Is the atom excited at this time, or is the atom excited at the other time? Now, if we ask, what is the probability amplitude for the atom in the excited state or the atom in the ground state? Well, we have the atom described by the state ket, and then there's also the state bra, which is the adjoint of the state ket. And I don't put any labels in here because that's just the state that we are talking about. And now, if I'm asking what's the probability amplitude for the atom being excited or for the atom being in the ground state at a certain time, well, I will have to look at the bracket of the ground state at that time with the state ket. And so this will be the probability amplitude for the ground state at time t. And following standard notation, let's just call this psi for the ground state psi g at time t. And likewise for the excited state, we will have a psi e at time t. And the two of them together make up a two-component object where we have the ground state probability amplitude and the excited state probability amplitude combined. And so this will be the wave function for this particular system. And of course, this psi, which is a two-component object, is itself a function of time. So let me just be careful and indicate this time dependence as an argument of psi. So this psi is a wave function, but in the simple case where we just have a two-state system, it has just two components, two probability amplitudes that compose the wave function. And of course, we remember what these probability amplitudes mean. If I'm squaring them, so I'm taking the square of the g psi of t squared, the square of this bracket, well, that's the probability of finding the system in the ground state at time t. And likewise, if I square the other component, the amplitude for the excited state, well, that will be the probability of finding the system in the excited state at time t. So we can now talk about following the system in time and assign probabilities for the ground state and the excited state as functions of time. In a situation like this, we usually know what are these probabilities amplitudes at the initial time, say t equals 0. So we know what is the psi for time 0. And we want to know what is the psi at a later time. So how do we find it? Well, we need to study the time dependence of these probability amplitudes, and the time dependence of these amplitudes really comes from the time dependence of the brass. So the Schrödinger equation for brass will apply. So let's see how this goes. Let's look at the time dependence of the probability amplitude for the ground state. So just copying what this is, it's the time derivative of the bracket. The bra depends on time, the ket does not. And so this time dependence of the bracket, well, that goes with the Hamilton operator. So we will have the Hamilton operator at time t sandwiched between the bra for the ground state at time t and the ket for the state. But what is this Hamilton operator? Well, remember what we said in the previous lecture, that the Hamilton operator that appears here stands for the energy of the system. And so now what's the energy that we associate with a system like this? It will be convenient to call the energy difference between the excited state and the ground state, call that h bar omega. So we are measuring the energy in units of h bar, and so the omega that appears here, that is a circular frequency, and that will become clear in a very short time. Okay, so this is the energy difference, and what will be the Hamilton operator that we write down for this system? So it will be, say, energy h bar omega for the excited state and energy 0 for the ground state. So the energy is 0 for the ground state, and it's h bar omega for the excited state. So in the excited state, we have the energy h bar omega, and in the ground state, we have the energy 0. So there's no such term for the ground state. So the Hamilton operator applied to the excited state, well, that will give us the excited state times its energy. The Hamilton operator applied to the ground state, that's the ground state, multiplied by its energy, which is 0. So this just gives 0. Yeah. However, we have to take into account that these kets and bras, they depend on time. So more precisely, I should indicate this time dependence and write it as such. So here you see what we discussed earlier when we talked about A of t, that this energy difference between the excited state and the ground state at any given time is always the same h bar omega. So this eigenvalue that appears here does not have a time dependence. Put differently, this Hamilton operator depends on time because the kets and bras depend on time, but the eigenvalues do not. So it does not have a parametric time dependence. Well, now with this Hamilton operator used here, applied to the ground state, well, we apply to the ground state, we just get 0. So now we continue, and we ask what's the time dependence of the probability amplitude for the excited state. Once more, we recall that this probability amplitude is the bracket of the bra for the excited state at time t and the ket for the state. So it will be, according to Schrödinger, it's the Hamilton operator applied to this bra, and then there is the ket for the state. Hamilton operator applied to the excited state, well, that gives us h bar omega. So here we get h bar omega, and then the excited state bra at time t. Well, that's just the probability amplitude that we started with, so it's h bar omega, the psi e at time t. So we can now combine these two equations into an equation for the wave function psi t with its two components, and that will read as I h bar times the time derivative of psi of t equal to, and now this is a two-component object, so we have a two-component answer here on the right, and that is 0 for the ground state, which is the upper component, and h bar omega psi e t for the second component, for the excited state. So I can move this outside, and then we just have 0 psi e t. So here is the Schrödinger equation for this two-component wave function as we find it from this Hamilton operator for this simple two-state system. Now, looking at it component by component, well, the time derivative of psi g of t, that's just 0, which says that the psi g at time t is the same as its value at the initial time 0. So this does not change in time. Now for the excited state amplitude, we have I h bar, the time derivative, is h bar omega, the function itself. So the h bar can be cancelled. This is one of the reasons why we measure the energy in units of h bar. And then we have an I left over here, which I get rid of by multiplying the whole equation by negative I. So after we have done that, we have the time derivative of psi e t equals negative I omega psi e t. And this has a simple solution too, namely the psi e t is equal to e to the minus I omega t, its value at time 0. So now putting things together, for the wave function as a function of time, that's equal to the upper component at time 0, and the lower component, that for the excited state, just gets multiplied by this exponential factor, which I can now write as a 2 by 2 matrix applied to the wave function at the initial state. Well, the wave function at the initial state is just the psi g at 0 and the psi e of 0, which are the ingredients here. The upper component just gets multiplied by 1, and the lower component gets multiplied by e to the minus I omega t. So, yes, by setting up the Schrödinger equation and solving it for this case, we found the time-dependent probability amplitudes. And of course, if we look at the probabilities now, the probabilities do not change. The probability for being in the ground state is this value squared, but since the ground state amplitude at time t is the same as the ground state amplitude at time 0, you square it, it's the same number. Probabilities of being in the ground state does not change in time. Same for the probability in the excited state. We have to square this number, so it's the square of the original amplitude, and the square of this complex factor, but this complex factor has unit modulus, so you square it, you just get 1. So in this particular case, these probabilities do not depend on time. In summary, we solved the Schrödinger equation for the probability amplitudes of a qubit and found their values at different times. In the next lecture, we use Heisenberg's equation to find the corresponding time dependence of the qubit observables.